Okay, this is Chapter 6, Thermochemistry, and this is going to be Lesson 1. And when we talk about thermochemistry, we're going to talk about chemical reactions and the energy changes that occur within them. So we have some important vocabulary words to define. The first one is force, and that's your typical physics definition. It's the push or pull on an object. So, for example, our gravitational force. And then we have work. And that is the energy used to cause an object to move against a force. And that actually has a definition that we're going to talk about a little bit later on, which is work equals force times distance. Moving on to heat. That's simply energy transferred between two bodies of different temperatures. And then energy, which is the capacity to do work or transfer heat. Continuing with some important terminology, we have kinetic energy, which recall is the energy of motion. And the formula is Ke equals 1/2 mv squared, where m equals mass and v equals velocity. And then we have potential energy, which is energy of position. And we call that stored energy. So I can have my book sitting on the desk, and that book has potential energy, stored energy. As soon as I take the book and it falls off the top of the desk, that potential energy turns into kinetic energy as it is now moving. And there's different types of potential energy. I'm going to mention a couple here. Electrostatic. So we can talk about the energy of an electron or a proton. Then we have gravitational. So as I had mentioned earlier, for an example, book on a desk. Then we have thermal. And that's due to the random motion of particles. And then one that we're going to be talking about the most probably would be chemical. And that can be either a battery, as in redox, or chemical bonding. Okay, so let's look at our roller coaster here to talk about the difference between kinetic versus potential energy. So over here on the left, we have the car, the roller coaster car, sitting still. The car has a mass of 1,000 kilograms, and 1 gram is 10 newtons per kilogram. So, number one, the driving force does the work on the car, and its gravitational potential energy is going to increase as the car is going uphill. At the highest point, the car has the maximum gravitational potential energy, okay, 45 meters, and it is stopped, so our kinetic energy equals 0. As it starts to come down over here, the gravitational potential energy is transferred to kinetic energy, and the car speeds up. Again, at the lowest point down here, our gravitational potential energy is 0, and the kinetic energy is 0 because it wouldn't be moving. And then it starts to go up again. So the gravitational potential energy is going to increase. But it's going to lose kinetic energy, okay, because the gravitational potential energy is increasing. So you can see it's a very useful way to explain the differences between the two. So when we talk about energy transfers and changes, we have to know some more terminology, and that is system and surroundings, because that's going to be determine what's happening every single time. So when we talk about the system, we're talking about the portion we're studying. And then the surroundings is everything else. And I know that that sounds like weird definitions, but it'll make sense in a minute. So when we're looking at a chemical reaction, so I have A plus B yields AB. Okay. So all of this, the reactants and the products, is the system. And then everything else, let's say this is happening in a beaker, okay? The beaker and everything else is the surroundings. And systems, by the way, tend to move toward the lowest possible energy state. Okay, I'm not sure when I wanted to do this, but there are some brief units that we need to discuss, so you might want to just write these off to the side. So energy units, because I just want to make sure that we cover them. So energy is measured in joules. So 1 joule, and I'm going to put in parentheses J because that's the unit, is equal to 1 kilogram meters squared per second squared. So what that means is, for example, moving a 2 kilogram mass at 1 meter per second has 1 joule of kinetic energy. Okay. We also need to know that 1 kilojoule is equal to 1,000 joules, and that 1 calorie is equal to 4.184 joules, and that 1 calorie is equal to 1,000. Oops, 1 kilocal, sorry. 1 kilocal is equal to 1,000 calories. Okay, so those are just some units that we may be dealing with in this unit, and I want to make sure I wanted to mention them. Okay, energy and the first law of thermodynamics. Very simple. Energy cannot be created or destroyed. So therefore, energy conserved. So energy lost by the system must be gained by the surroundings, and vice versa. All right, heat. We talked about this on the first page. Energy transferred from a hotter object to a cooler one. And then we have work, which is energy transferred when a force moves an object. So, there's 2 examples that I want to give here. One for heat and one for work. So work is done, as energy is transferred from a pitcher's arm to the ball. As he throws it really hard at the home plate. And then another example with heat. Just think of regular stove. Heat added by a burner will cause H2O temp to increase. So basically, causing motion of an object against a force, like the pitcher throwing the ball fast at home plate, and causing a temperature change are the two general ways in which energy can be transferred in or out of a system. Okay, so let's talk about internal energy now. Internal energy is the total energy of a system. So this is the potential energy plus the kinetic. Now, it's very difficult to measure the total energy of a system, but we can measure the energy change. So this says dE, delta, but it's I can't make the triangle, so it's going to be delta E. So this is the same thing, delta E. So the change in energy is equal to the final energy minus the initial energy. And this change in energy has magnitude, meaning a value, quantity, sign, it's either positive or negative, and it has a unit, either joules, kilojoules, cal, depending on what the problem says. So, a couple of things that we need to remember is your delta E is negative when your energy final is less than your energy initial. And delta E is positive when it's the opposite, when your final is greater than your initial. So that's something that's kind of intuitive if you think about it, actually. So in chemical reactions, we're studying energy changes. And the initial state refers to energy of the reactants, which should make sense. And the final state is energy of the products. Couple more things I need to cover. I'm just going to move this up a little bit. When we have a negative delta E, then you know that it is exothermic. And energy is lost to the surroundings. And then when we have a positive delta E, we know it's endothermic. And energy is gained from its surroundings. Okay. So this is supposed to be change in potential energy. And this is also over here, change in potential energy. So potential energy that's stored in the chemical bonds is converted to kinetic energy as heat. And this is just showing you exothermic. The energy is being released, and endothermic, it's being taken in. So our change in energy, we're going to cross this out, some typos here. Our change in energy depends on energy conversions and exchanges in a system. And the equation is delta E equals Q plus W. Where W is referring to work and Q is referring to heat. Okay. Now, there's some sign conventions for Q and W that if you can remember them, it makes things easy. But I'm going to explain it as well. Heat added to the system is going to be positive. Heat removed from the system is negative. Work done on the system is positive. And then work done by the system is negative. So here you can see, I was looking for a highlighter, I didn't see one. On this one, when we do something to the system, either add something to it or do work on it, it's positive. If we're removing or work is being done by the system, then it's negative. And that picture basically explains it all. Here you have work being done on the system and work being done on the system and heat being added, positive. And then negative is, well, they have this arrow wrong. Isn't that funny? This arrow should be going this way. Needs to be going into the system. Hopefully, I believe it's right on your PowerPoint. Your paper, it's just not showing up right here. There we go. All right, last slide. So let's do some sample calculations for the change in energy. A system does 195 kilojoules of PV work and absorbs 38 joules of heat. So the system's doing work, so that means that my work is going to be negative 195, and it absorbs heat. So my Q is going to be positive 38. So when I look at my equation, delta E equals Q plus W, this is going to be 38 joules plus a negative 195 kilojoules. So notice we have disagreement of units. So I'm probably just going to go back and do this in my head. 195 kilojoules is the same as negative 195,000. 195,000. So negative 1950. There we go. Now we have agreement of units, joules. So our final answer is going to be negative 194,962, or approximately negative 195 kilojoules. So now I changed it back. And you have to look at what they're asking you to do in the problem so you can determine the units. Let's look at the next one. A chemical reaction in a piston chamber gives off 500 joules of heat to its surroundings. So you know right away that this is going to be negative. The expanding gas moves the piston upward. So the piston's moving up. It's part of the surrounding, so it's going out. So this is also going to be negative. So if I write my equation, I've got delta E equals negative 500 minus negative 240. And these were both joules, so it's simply going to be negative 740 joules. Not kilojoules, because they were both in joules. Pay attention to the units. All right. And the last one. The chemical reaction from B was rerun with the piston in a locked position, and now this time it generated 740 joules of heat. So it's generating, which means it's giving off. So this is going to be negative. The piston is locked, so it can't do any work. So work is equal to 0. So you've got delta E equals negative 740 plus 0. So it just equals negative 740 joules. All right, and that's it for lesson 1.